Okay, as we go through today, if you have any questions, send them in using the question and answer window. That is the window I can see as I'm giving this presentation. If you raise your hand or you send it via chat, I probably won't see it until the end, if at all. But without further ado, let's get started. Today's webinar is about Wi-Fi. So the purpose of today's webinar is to try to sort of demystify Wi-Fi, right? Wi-Fi has been around for a long time now, over 20 years. I think we're getting close to 25 years, but it's something that can't be seen and it doesn't always behave in the way we think it should. And it can often be really difficult to figure out, what's going on when it's not working the way you think it should. So today we're going to go through, it's a high level overview. We do get technical in a few parts, but don't worry about needing to necessarily fully understand and memorize this. It's just to give you a better idea of what's going on, why certain things happen the way they do, and just some, towards the end here, just some general purpose best practices and what to do when you're deploying Wi-Fi at your customers' locations. So for those of you that aren't familiar with Zyxel, we've got just one slide here to give a sort of a brief overview of who we are. So we've been making computer networking and products for over 30 years now. We started way back in the late 90s. Excuse me, yeah, late 1980s. Is that right? That's right, yeah. It's a long time that we've been doing this. We are a global company. We sell our products in 150 different global markets. We have over 100 million devices deployed out in the field. The US location is based out of Anaheim, California. That's our sales, that's our marketing, that's our warehouse, and that is our tech support. So when you do call in to get tech support, you are talking with a Zyxel employee here in the United States. So that's it for the background on us. Now let's start talking about Wi-Fi, which is why you came here today. So we'll start by talking about the main players when it comes to Wi-Fi. There's three names you're going to see out there a lot of the time. The first one is the IEEE. So the IEEE is an engineering group that creates standards that apply to networking. They're where 802.11 A, B, N, AC, AX. That's where these names come from. These are the definitions from the IEEE that define the standards, which then get turned into stuff like Wi-Fi 6, Wi-Fi 5, etc. There's the Wi-Fi Alliance. So they're the ones who will give you these Wi-Fi certified logos. So the Wi-Fi Alliance is primarily a marketing organization for the industry that went out there and tried to brand Wi-Fi and educate the consumer. So one of the problems they ran into with early Wi-Fi products is that there is still incompatibilities. Despite all the time IEEE spends on defining the standard, there's always room for interpretation where one company may interpret something different than the others, or areas where things may not have been as defined as they should be. So the Wi-Fi Alliance got together and decided to offer Wi-Fi certification, where they do interoperability testing, mandate certain parts of the spec, that should be mandatory, help try to clear up any misunderstandings. So that's why you will see the Wi-Fi certified logo on certain products. Those are companies that have paid the Wi-Fi Alliance and submitted the product for this testing as a way just to ensure that it is going to be interoperable. In general, the Wi-Fi Alliance certified logo is something you primarily see on consumer products. You don't see it as often on business class products. And then there's the FCC. So that's obviously the federal government. They manage and monitor our RF usage. So they define what frequencies can be used, whether or not a license is required, power output, and other sorts of behaviors of the actual RF characteristics themselves. So these three things combine to regulate and define what goes into a Wi-Fi product. So Wi-Fi itself uses radio waves. So it's the same, roughly the same technology as your radio, over the air broadcast TV, as walkie-talkies and things like that. So just in a general rule, as frequency goes up, the more data that can be encoded onto that. But also as frequency goes up, the lower the range. So a good example of this is just radio waves, right? AM radio is lower frequency. So that's why you don't get a lot of music channels on AM radios, because it doesn't sound as good as FM radio. However, if you've ever gone on a road trip out into the countryside, you may have noticed that you can pick up AM stations from a lot longer distance from their source than you can FM stations. I know, in Bakersfield, it's very possible, and even sometimes here in Southern California, it's possible for me to pick up San Francisco's AM radio station, and have it be perfectly legible. Whereas FM, you're never going to get that far with the frequency. And that's because FM frequency allows them to cram more data on there, gives us better quality, but again, the signal doesn't go as far. So radio frequencies are regulated by the FCC, and in order to broadcast in general, you need a license. So the FCC has carved out some parts of the spectrum for basically end users, consumers to be able to use without requiring a license. So let's get the laser pointer right here. So there's the 900 megahertz spectrum here. This was really popular back when I was a kid for cordless phones. Got you some fantastic range, not a lot of quality. Starting in the late 80s, early 90s, you saw cordless phones move to the 2.4 gigahertz spectrum. And this is probably the most famous spectrum that most people are familiar with when it comes to using Wi-Fi devices. So that's 2.4. And then you've got the 5 gigahertz spectrum here, which is a higher end spectrum. And you saw in the early to mid 90s, a lot of cordless phones moving to that. So, why did cordless phones move to these? Because sound quality was more important than range in general. Most people are not needing to, walk across the street to their friend's house on a cordless phone, something I was able to do as a kid with a 900 megahertz phone. So you get better sound quality. They also implemented better security. But the other problem was just the bandwidth available. If you lived in an apartment building or a condo or near one, the amount of bandwidth quickly filled up as to how many people could be using a cordless phone at once before they started interfering with each other. So each of these different jumps up in spectrum also increased the amount of spectrum that was available. So the more spectrum that's available, the more people who can use it at the same time before there's some sort of interference. So Wi-Fi uses the 2.4 and 5 gigahertz spectrum, just like cordless phones do, and a number of other different consumer devices that use wireless RF. So when you're looking at data sheets for products, you'll probably notice one of two things. The power or the strength of an access point or router is normally either mentioned as being milliwatt or dBm. So basically, there are two different ways to denote the same sort of thing, which is the power output of your device. So consumer products tend to use milliwatt versus dBm for the simple reason that basically for every 3 dB increase in dBm is a doubling of your milliwatt output power, right? So to go from 20 to 23 dBm output power takes you from 100 to 200 milliwatts of output power. And obviously, from a marketing perspective, it's a lot more impressive to say, look, ours is 200 milliwatts of power versus our competition who's only at 100 milliwatts, versus saying we're at 23 and they're at 20, right? So it's a much more marketable term to use milliwatts. Generally, though, on business class products, when you look at the data sheets, you'll see dBm used because that's what's used generally when it comes to engineering. It's much more a realistic measure of sort of like the differences in what you could expect to see as far as range. A consumer sees 200 versus 100, they assume they've got twice the coverage distance, which isn't the case because the RF signal degrades quite rapidly as it radiates out. Also, the nice thing with using dBm is you can quickly add the dBm coming out of the chip to the dBi or antenna gain that you would get on an external antenna or even an internal antenna to make it really easy for you to calculate links. So for instance, if you're doing outdoor point-to-point, you take the chip output power, you add the antenna dBi, you subtract any loss from the cable runs and the connectors, and you can really easily simply add in and subtract to get what your total radiated output power is at the point of the antenna. So it's really nice for doing calculations and things like that. So some other terms you will see when you start getting more into Wi-Fi is signal to noise ratio. So a lot of people spend time looking at the output power of the chip, right? That milliwatts or the dBm output power of their access points or their routers, or maybe looking at the receive sensitivity. But really, the signal to noise ratio is what defines how fast that Wi-Fi signal is and how how reliable it is. So that's basically saying the strength of the signal versus the level of RF noise. So no matter where you are, unless you're way out in the middle of the forest someplace, there are other sources of RF noise using the same frequencies you are. As we talked about earlier, 2.4 and 5 gigahertz is free to use for Wi-Fi. It's free to use for cordless phones. And there's all sorts of other devices that you may be using that are using wireless to communicate. Things like microwaves use the 2.4 gigahertz spectrum to heat food. So they will leak out radiation using those same RF noises, same RF signal that you're using for your Wi-Fi. Um, Industrial equipment tends to put off RF radiation. So a lot of stuff out there that can be causing noise. Um, so when you're looking at things, the signal to noise ratio is really what defines the quality of your connection that you can expect. Another thing to keep in mind is attenuation, basically how much the signal degrades. Essentially, as you travel through a medium, the signal degrades with distance. So the thicker and more solid that medium is that it's traveling through, the more quickly it's going to degrade. So for instance, dry air isn't going to degrade the signal very quickly. Wet air, wet humid air will degrade the signal more quickly. If it's raining or snowing, that will degrade the signal. If the signal needs to pass through a wall or glass, that will also degrade the signal much more quickly than if it was going through open air. So for those of you wanting to try to calculate how far your signal can go, this is the formula here. I won't go through that formula, but if you're doing outdoor links, if you go and Google basically the distance, there are calculators that you can use for free on the internet to try to tell you how far your signal can go. But generally, they don't take into account signal to noise ratio. So this is really key. So what a lot of people don't know is a simple 100 milliwatt access point or router, in theory, can send its signal and make a reliable signal over 1 mile. Now, realistically, if you've ever done anything with Wi-Fi, you know you are not getting a mile's range on a router, a consumer router. And the reason for that isn't because of the signal; it's because of the signal to noise ratio um, affecting things and basically raising that noise floor, so your device can no longer differentiate between the signal it wants to hear and the just general level of noise that's available out there. So anyway, there's a couple different things here on the screen showing you, how much different materials can degrade the signal strength. So for instance, just a standard glass window gives you a 3 dB loss in signal strength, or basically a 30% reduction in the range. A tinted window, something that's got a coating on there to keep out ultraviolet or keep out infrared, can get all the way up to 8 dB. So some very significant differences there as far as just the material that it's made out of. And then the same thing, you go look at your walls here. Um, Walls will do the same sort of thing. The thicker and heavier the wall, the more it's going to degrade that signal. And metal, just in general, is horrible, especially not necessarily even thick metal, but if you're doing something with mesh, any sort of mesh like a chicken wire, it tends to be really good at blocking signal. So that's a problem we have here in Southern California, because everything is stucco, or at least just about, it seems like every residential building is made out of stucco around here. So stucco is basically stick based. I guess you call it support. Then they run what's essentially chicken wire across the wood, and then they coat that with cement. So that chicken wire, not the cement they lay onto it, really, really tends to block signals from leaking out. So now when we're talking Wi-Fi range, um, so one thing, we've talked about here is signal strength, signal to noise ratio, attenuation, frequencies being used, and how all of that will affect range. The other thing to keep in mind, which people tend to forget about, is that Wi-Fi is two-way communication. So the range is really defined by the weakest member that you're communicating with. So for instance, really normal these days to find an access point with 500 milliwatts or stronger signal, whereas a mobile device, a cheap Android phone, even some iPhone devices, um, max out their power at 25 milliwatts. So your access point is able to shoot that signal really, really far, but it does no good if it can't get the signal back from the device it's talking to. So, a good way of thinking about this, or a metaphor for this, would be just, holding a conversation with somebody. If you've got a nice, healthy voice, you can raise your voice and you can shout very far. But if the person you're talking with has a sore throat and they aren't capable of shouting or raising their voice, right, you have to get closer to them, even though you can shout and people a long ways away can hear you. So it's the same sort of thing. So it's just something else to keep in mind. So a very common problem people run into with this is, you'll be using Wi-Fi on your phone, and you'll notice that your Wi-Fi is really poor. It's really slow. You're having issues connecting. You're getting timeout messages. But you look at the top of your phone there where it shows you that you're connected to Wi-Fi, and it shows you've got a solid, 2 bars, or somewhere in the middle there, depending on how your phone designates and shows the signal strength. And the reason for that is because your phone is showing you the signal strength of the signal from your access point, and it can hear your access point fine. I mean, it may not be full 5 bars, but it should be, you would think, good enough. And the reason it's not is because your access point isn't able to hear the signal that's being sent back from your phone. So the phone's only showing you the signal strength that it hears. It has no way of knowing how strong the signal is back at your access point or router that you're connecting to. This also causes issues, especially in office buildings and stuff like that when you're planning things out, because people tend to basically, you know, plot their APs based on where the client devices are. So the AP may have perfect coverage for that client device, or the client device has no problem reaching the AP, but the problem is the AP signal is shooting out really far, and it can be causing interference with access points a long ways away in the building. And we'll talk more about that later. We'll talk a little bit more about smart antenna and how that sort of helps solve this issue. But that is another cause of interference that people tend to overlook, is just not realizing just how far their AP or router signal can go and cause interference, even though the connection isn't usable at that distance. So some other RF behaviors, we call them radio waves, right? And radio waves largely behave the same way that waves do in water. So it's a good analogy to sort of think of a pond with water and what happens when you throw a rock in that pond, causing it to generate waves. So the same things you will see in that pond are the same sort of things you would see with RF waves if you could visually see them. So basically, we've got our transmitter here. It sends out the signal. So as it hits a solid device or a solid obstacle here, it will go through that obstacle, depending on what it is, obviously, but it's going to be attenuated and weakened. It may hit other objects in the area, such as a wall, and bounce off of them. It can also scatter. So one wave will hit something and it will reflect and break up into multiple smaller waves going in different directions or slightly offset. So these are all sorts of things which can cause problems. And we'll get more into this a little bit later here. Another challenge that faces Wi-Fi was, until Wi-Fi 6 came along, we've been using basically the same algorithm for handling who gets to transmit, as we've been using in Wi-Fi since 1997, when the first Wi-Fi spec was ratified. So it had never been changed in all of these years. And this is another common cause of problems that people run into. So in general, with radio waves, only one device gets to transmit at a time. If two or more devices transmit at the same time on the same frequency, those signals cross and interfere with each other. The packets get dropped. So if you grew up as a kid and you had analog walkie-talkies, you probably encountered this, if you had more than two, where two people would try to talk at once, and the person who was listening would just get a bunch of garbled nonsense because those two signals were interfering. It's the same thing with Wi-Fi. So the way Wi-Fi back in 1997 was defined, is to how to determine whose time it is or whose turn it is to be able to broadcast, was this very simple flow chart here. Basically, you need to transmit something. you sense the medium. So what that means is that basically you listen, is anybody else talking? If no one else, or excuse me, if somebody else is talking, then you use a random number generator. It'll generate a certain period of time, and then you will wait that period of time before listening again to see if it's your turn to transmit. If you listen and you don't hear anybody, then you go ahead and transmit the data that you want to transmit. So one of the problems we run into here with Wi-Fi is, right, it was back in 1997 when you were doing and using Wi-Fi, it was really slow. Streaming audio and video and stuff like this was not a common practice. It was just designed for sending small amounts of bursty data. So this worked generally pretty well back in those days. But obviously, as we go today, people have more and more devices that they're using and connecting in their home. So as you increase the number of users and you increase the activity of those users with something like streaming, where you're constantly sending or receiving data, you increase the chance that two or more devices are going to listen or are going to decide that they want to send data. They will both listen at the same time. Both will see that there's no one else transmitting, and both will decide to transmit at the same time, causing interference and causing those packets to be dropped. So this is one of the challenges we have with Wi-Fi, with doing voice over Wi-Fi, because this is not very voice friendly. So voice, even though voice data over Wi-Fi is using less than 100 kilobits per second of data to send its, the voice, it's a very small, low bandwidth application. It's a constant application, and it's an application where if packets come in out of order, that's not tolerated. And if there's any sort of delay in getting those packets, it's not tolerated, right? So voice is very particular. Those data packets must reliably come in order. So this is where the challenge runs into, is with Wi-Fi, is this, you run into issues where packets get dropped because two or more devices decide to transmit at the same time, or somebody else is transmitting and you don't know how long you need to wait. So you use a random number, which is less than efficient. So it causes issues with jitter and things like that when doing voice over Wi-Fi. Another problem that goes into this, which is very similar, is something called the hidden node problem. So you've got your access point here in the center of your room. On one end of the room, you've got a wireless client. On the other end of the room, you've got a wireless client. Both of these devices are within range of the access point. So the access point can hear them, but they aren't within range of each other. So what happens in this situation is this guy here listens. And even if this guy over here is transmitting, he doesn't know it because he can't hear this person, but the access point can. So he'll think the airtime is free and he'll start transmitting, causing interference. So this is something that happens a lot in bigger areas where you've got a large coverage area that you're trying to cover. Very similar to the previous issue we were talking about. So it's another problem that causes issues with Wi-Fi deployments. And again, as you add more devices onto the network, the more likely you're going to run into this sort of situation where the clients can't necessarily see each other to be able to do that check to see if someone else is already transmitting. All right, one more sort of term to go through. I'm calling it here data rate versus throughput. These aren't necessarily the correct engineering terms to use, but these are the terms you will see out there on Amazon and on websites in general. This is how they're usually used. So when you're looking at Wi-Fi specs, when you're looking at a data sheet for a product, they'll normally talk about speed as the data rate. So this can also be, depending on whose document you're looking at, can be referred to as a physical rate or a link rate. And this is a measurement of the amount of data that is sent between two different devices. So this is all the data that is sent from one device to the other when they are transmitting. When people get devices in their home and they do speed tests on them, they're measuring what we're going to call throughput. So throughput is looking at the data that you want to send between different devices. So throughput, for instance, let's say you transfer a 1 gig file from your PC to a NAS. So you will look at that and you will see how much time it takes to send that 1 gig file, and that's where you'll define your throughput. What throughput leaves out, though, is all of the additional overhead that goes into making Wi-Fi work. So Wi-Fi, um, has a ton of what we call protocol overhead that allows Wi-Fi to work the way it does in this open, unlicensed RF spectrum that's subject to interference from so many different places and just things in the environment which can degrade that signal. So because of all of those problems, there's a lot more overhead you get with Wi-Fi than you would get with, say, a solid wired Ethernet connection, right? With an Ethernet connection, you've got a dedicated medium that doesn't have to worry about outside interference and playing nicely with other devices. So because of that, there's very little protocol overhead, and there's very little difference between the data rate and the throughput. So between how much data you actually want to send versus how much data actually gets sent by your by the network card. Wi-Fi is the opposite. Wi-Fi has got a ton of this protocol overhead. So generally, because of this, when people do speed tests, even before taking into account distance and RF environments and variables and things like that, it's pretty much normal that you're going to see about a 50% hit or more between the advertised data rate and the throughput that you're able to achieve when using something like a speedtest.net. So if you go through Amazon, and you can pull up any basically wireless device and read the negative reviews, and a huge chunk of them are people complaining about this, the fact that we're misleading by advertising the data rate when you can't achieve that with your throughput test. But this is why. And this has been the standard using data rate to define the speeds for any sort of network device, whether it's a wired device, a wireless device, power line device. All of them will use the data rate because that's what's defined in the spec. And that is truly what is being transmitted back and forth between those two devices. That's how much data and how fast that data is. It's just there's a lot more data being transmitted than you realize because of the protocol overheads. Okay, so that's it as far as terms and stuff goes. So now I want to talk about increasing speed. So this isn't how you would increase speed in your deployment. This is how the industry increases speed between these different Wi-Fi standards and why one device has a different speed than another. So there's three primary ways in which speed can be increased. The first one is increasing the encoding. So 11N use 64 QAM, 11AC use 256-bit QAM, 11AX uses 1024-bit QAM. So this is basically how much data we can cram in the same amount of space. So as you increase the amount of data you can cram on there, it also requires a lot more horsepower to be able to do that. The other thing is what we call spatial streams, and we'll go more in depth into what a spatial stream is. And the other way of doing it is by increasing bandwidth. So the big difference between 11G versus 11N speeds was the fact they doubled the amount of bandwidth. So in 11G, you could only use approximately 20 megahertz of airtime at a time. With 11N, they doubled that to 40 megahertz of airtime. And with 11AC, they bumped that up theoretically to 80 megahertz with the original 11AC products, or up to 160 megahertz with the Wave 2 products. So now let's try to explain some of these for you. So one thing we do need to know is we do need to know how airtime works and bandwidth and stuff works. So in the United States, 2.4 gigahertz has essentially 60 megahertz of bandwidth available. So what you will see here, though, is that when you look at your, your GUI and the router AP, you will see that you've actually got 11 channels to choose from. The problem is these channels you choose from are actually only spaced apart by 5 megahertz, but you're actually using a 20 megahertz size channel. So these channels actually overlap with each other. It can cause interference if you've got two devices on overlapping channels. So realistically, using 20 megahertz channels, which was common with 11B and 11G, you've only got 3 channels you can use in North America without causing interference. Channel 1, channel 6, and channel 11. Any other combination of channels being used in a multiple AP environment is going to cause some level of overlap and interference between these channels. So with 2.4, 11N gave us the ability to use 40 megahertz channels, which is great, right? You've doubled your speed. However, you've only got 60 megahertz of frequency that's available for everybody to use. So what happens is if you're in a house that's on a a chunk of property, you can use 40 megahertz, no problem. But if you live in a more traditional residential area where houses are next to each other with very little space between them, or worse, in an apartment or condo, 40 megahertz channels are basically unusable, because as soon as you add a second person with an access point or router using a 2.4 gigahertz to communicate, you're going to have overlap, which is going to degrade the performance of that 40 megahertz channel. So the way to get around that, and this is why there was a big push in the later days of 11N to dual band access points and radios, was the move to 5 gigahertz. So whereas 2.4 had only 3 non-overlapping channels to play with, 5 gigahertz gives us over 20 non-overlapping channels to play with. Right, so you've got a lot of channels to choose from. So that solves this interference issue, at least at first. There's a couple things we need to talk about here. The first one is, you will notice a huge chunk of these channels are in orange instead of green. And we note here that these are what we call DFS channels. So what is that? Basically, when the FCC decided to open up the 5 gigahertz spectrum, there was one problem. There were already other devices using this 5 gigahertz spectrum. The most common being radars, both weather radar and the radar used at airports for air traffic control. There's some other stuff as well, but these are the two major ones. So the way the FCC determined, how do we do this? How do we allow people to use the same spectrum that's already being used? And so they developed something called DFS. I believe it's a dynamic frequency something or other. So basically, in order to use one of these DFS channels, your device first needs to monitor that channel for a certain period of time to see if anybody else is using it. If it detects somebody else is using that frequency, it must find a new channel to switch to. And if it's also a DFS channel, it needs to pause and monitor to make sure it's not being used by radar or something like that. So it adds another layer of complication. It can also add a little bit of delay. So one of the challenges we run into here is that a lot of consumer grade equipment doesn't support DFS. So this causes us issues a lot of times, and it generates a lot of support calls to us, because we'll have people call and complain and say, hey, look, I'm using your access points in my building. 90% of our devices are connecting to that access point just fine, but Bob's laptop or Tom's tablet aren't able to connect. There's a problem with your equipment. Why aren't you compatible with their device? And usually what we do a little troubleshooting, quickly find they're using a DFS channel, and that laptop or that tablet or that whatever is a consumer grade equipment that somebody bought. It doesn't support those DFS channels, so it's unable to connect. So that's one problem you run into with DFS. The other thing again is as soon as radar is detected or some other legacy 5 gigahertz signal is detected, you have to switch channels. So that also causes issues, right? So you're using your 5 gigahertz thing. We detect, hey, there's what appears to be, it may just be, industrial interference, but it appears to be a legacy 5 gigahertz device. We now have to switch channels. So we have to disconnect everybody, find a new channel. And then again, if it's a DFS channel that we then move to a different DFS channel, we then have to stop and monitor for a little bit before we can actually turn it on and start using it again. So you get a lot of customers complaining, hey, I keep getting disconnected. It comes back after 30 seconds, but it's really annoying. And again, we find generally what happened is they're using DFS and the device is detecting legacy 5 gigahertz usage, so it's having to switch the channels. So these are two reasons why people don't necessarily want to use these DFS channels. So something that you have to always take in mind when you're planning out which channels you want to use on your 5 gigahertz APs. And if you're using our Nebula platform, you can go in there and you can tell it whether or not, set it to automatic channel selection and tell it whether or not it can use DFS. So that's something that you can choose. So the next thing to talk about here, right, is we're talking about bandwidth. So these are, 20 or so non-overlapping channels that are available assuming you're using 20 megahertz channels. But again, the way we've been increasing speed largely from 11G to N to AC has been by increasing bandwidth. So if you jump up to 40 megahertz channels, right, you basically are cutting in half the number of channels that are available. And if you're trying to avoid these DFS channels, you're down to just 4 non-overlapping channels that you can use when you're planning your deployments before you start getting RF interference. Then we've now got 80 megahertz channels with 11 AC. And again, you're now down to just 2 non-overlapping channels before you start encountering interference. And if we go up to 160 megahertz channels, you absolutely have no choice but to use DFS channels to be able to get these higher speeds. So what happens a lot in the real world is the product is advertised based on 160 megahertz channels, but you may not be able to use these in your deployment. So you're only using, say, 40 megahertz channels. So you're basically dropping your maximum theoretical speed by 75%, right? By dropping from 160 to 40. So now let's talk about spatial streams. So as we were talking about before, RF sort of radiates out like a wave from a rock thrown in a body of water. It hits different things and can reflect off of them. So in this scenario we've got here, here's your AP, here's your laptop or whatever your client device may be. We send out a signal. So this signal is going to get there first from the direct signal, right? It travels through the open air, gets to the device. But the same signal is hitting walls and furniture, bouncing off of them and then reflecting. So because the path is longer, right, it goes off not towards your client device, hits something and then reflects towards the client device over here, you end up in a situation where you get what are essentially echoes, right? You get the main signal that you hear, and then you get this echo from the sound also bouncing off, or the RF bouncing off other objects in the area, just like sound does in a canyon or in a gymnasium or something like that. So this is what we call multipath. So multipath was the bane of Wi-Fi back in the single radio 11 and 11G days. Some smart engineers, though, developed some technology that allows your devices to determine what is an echo and what is not an echo. So they can sort of ignore that. And then other smart people came along and they said, well, wait a minute. What if we take advantage of these echoes to increase the amount of data we can send? And the way they do that is by taking advantage of multiple antennas, both on the transmit and on the receive side. Because those antennas are physically spaced apart from each other, they are going to follow slightly different paths. So you're able to send data simultaneously on two different antennas. So different data simultaneously at the same time, taking advantage of the fact that there's this slight echo effect and being able to differentiate those echoes. So if you have 2 antennas, you could theoretically transmit 2 different streams of data at the same time, and then the client device combine those together to one faster bit of data there. So the main way that this was done was what we call MIMO, multiple in, multiple out, allowing us to increase speeds. With 11 AC Wave 2, they introduced something new called MIMO, multi-user, multiple in, multiple out. So we're still using those same different data streams, spatial streams, but now what we're doing is we're sending different data to different client devices. So you could use one stream to send data to one device and the other stream to send data to a separate device, allowing your AP to send data to 2 or more devices simultaneously, depending on how many spatial streams your access point or router supports. So this was something new that was allowed in the 11AC. So this MIMO technology kind of allows us in some ways to be able to break this rule, one device transmitting at a time, depending on how it's implemented. So that's one way. Another way we've increased speeds is by these spatial streams. So when you're looking at data sheets, particularly for business class products, you will often see the Wi-Fi speed designated not as megabits, but as by spatial streams. You'll see a 2x2 or a 3x3. So basically the first digit here is how many spatial streams you can transmit. Second number is how many spatial streams you can receive. So on access points and routers, these numbers are usually the same for both. However, on client devices, particularly small mobile devices, you will see oftentimes this first number is smaller than the second. So your client device can receive for say 2 spatial streams, but it may only be able to transmit 1. So it can listen at fast speeds, but when it talks back to the access point, it talks back at a lower data rate. And then if you're looking at say some stuff out there, particularly Cisco equipment, you will see something like this down here, 4x4:3. So that's telling you you've got 4 antennas that can transmit, 4 antennas that can receive, but you can only actually use 3 of them at one time. So arguably this gives you a little bit more flexibility in which antennas you're using to transmit and receive to help with, you know, adapting to the RF environment. But realistically, it's more of a marketing gimmick in the real world than it is anything else, right? Because people will see one device being advertised as 3x3 and another as 4x4:3, and they'll focus on just that 4x4 and go, wow, I'm getting an extra spatial stream, right? It's 25% faster. But in reality, that :3 is really the most important thing there, telling you that you've only got 3 spatial streams actually usable. So it's essentially the same thing as a 3x3. So putting it all together, your maximum data rate that you will see advertised is a combination of spatial streams, modulation type, and how big the bandwidth is. When you're looking at a device, looking at a data sheet, looking at an online listing, they'll always focus on the maximum of all of these, the maximum spatial streams combined with the maximum QAM, combined with the maximum bandwidth that gets all together to get that maximum speed. So instance here, if we've got a device with 1 spatial stream, it's 11 AC device, you will see it advertised as AC 900. They'll round up this 866 to 900, you know, but in the real world, for instance, you know, if you can't use 160 megahertz channels, it'll drop back to a slower 80 megahertz or 40 megahertz. If the signal to noise ratio and this is kind of misleading because people will simply look at the data sheet and the data sheet will have some ridiculously large number like 128, 256, 512. So that is the theoretical maximum number of clients you can get on that access point based on basically how much memory is dedicated to the association table. How many different APs or devices can that AP track at a time? But realistically, you're going to have issues long before that. And usually those issues you run into have nothing to do with the hardware on your AP or router, but have to do with the way 802.11 works. So generally you're going to hit those the limitations of the Wi-Fi spec itself long before you hit the limitations as defined on the data sheet. Right. So that's why the data sheet may say we support, you know, 512 devices, but we will tell you when planning things, we'll, you know, plan on having, you know, around 24 users per AP or less, depending on the application. So here's how we try to explain that here. So here's a scenario that we run into. So in this scenario, clients are connected with a negative 67 dBm signal strength. They're using 5 gigahertz, 20 megahertz channels. So between each of these scenarios, the only thing we are changing is the number of spatial streams supported on the client device. So in this case, using 3 spatial streams, watching a 3 megabit per second video stream, you're able to fit 34 laptops on that access point without any issues. You're getting an aggregated here 100 megabits overall data rate that that access point supports. Simply change the client to a client device that only supports 2 spatial streams. And now the maximum number of connected client devices is just 21 with an aggregated 65 megabits aggregated data. Drop it even more to a device that only supports a single spatial stream, and now you've only got 10 devices that can connect to that access point before you start having issues. So that's just changing one variable spatial streams. In the real world, not everyone's watching the same stream, not everyone supports the same number of spatial streams, not everybody has the same signal strength. So in the real world, it gets really messy really quick. But the main takeaway here is, in general, the data sheet isn't going to help you. And in fact, which vendor or which model you choose isn't going to really have much of an effect on how many devices you could use on that access point, because you'll start running into limitations based on what we were talking about before, airtime utilization and how optimal that is, the types of data that are being sent, et cetera, long before you get to whatever the data sheet says is the maximum number of theoretical connections. So now I want to talk a little bit about co-channel interference and how we sort of solve that with smart antenna technology. So co-channel interference, we've talked about it already a lot today. It's basically when you've got multiple devices transmitting at the same time on the same channel. It causes interference, and those other devices could be a long ways away, especially when it comes to access points and routers. Those signals can go really, really far. So the traditional way you dealt with co-channel interference is very careful channel planning, right? You would plan out where each AP goes, and then you would try to choose non-overlapping channels and plot that out. If you were still having RF interference issues, what you would do is you would then drop the power output of your access points, which absolutely works. It will reduce co-channel interference, but it will also lower your signal to noise ratio, right? Because of you might be getting rid of the noise floor, you're also getting rid of the signal strength. So oftentimes lowering power would simply exchange co-channel interference for other signal to noise ratio related issues. So you might not necessarily see that much of an improvement, or maybe even worse, depending on the specific application. So smart antenna is how we sort of solve this. So here's your traditional access point. It's designed to be installed on a ceiling in a central area, and it sends its signal out in roughly a circular pattern. For outdoor applications, you get directional antennas, which focuses the signal in one specific direction. So what smart antenna does is, instead of having this one fixed antenna pattern, we actually have the ability to go through hundreds of different antenna patterns for each individual client device. So our algorithm that we use takes a look at where the client device is in relation to the access point and focuses the signal towards it. But in addition to that, we look at for other sources of RF interference and make sure that when we tailor the signal, we're doing it in such a way to take into account not only where the AP or the client is in relation to the AP, but also where this other noise is, and try to focus so we aren't listening and picking up that RF interference. So this works regardless of client device. It doesn't require the client device support any special technology on their side of things. It works in real time, even with client devices that are in motion, constantly adjusting the antenna pattern based on the real world best application. So here's a test scenario. This is using our wall plate AP and using a ubiquity wall plate AP, which spec-wise is basically the same thing. The primary difference between our device and the ubiquity device is smart antenna versus non-smart antenna. So this is a hotel or MXU application here, where each room gets its own low-powered access point We're using 5 gigahertz, so we've got a lot of channels to choose from here to space things out, and we're avoiding DFS channels because this is an end user thing and a lot of end user devices won't support them. So when we have just one AP, what you see here is performance is basically the same. In fact, technically the Ubiquiti outperformed us, getting 406 megabits data through aggregated throughput versus 404. So now once we add in a second AP, this is where the smart antenna really starts to shine. So what you will notice here is when we've got two APs functional, the aggregated throughput between both of them, the Ubiquiti is just at 550 megabits per second, whereas the Zyxel with smart antenna aggregated throughput is 785 megabits per second. If we look down here on channel efficiency, you will see the Ubiquiti APs combined are using 95% of the available airtime. Zyxel is able to use 131% of the theoretical 100% maximum that you can achieve. So how is that possible? And it's because the smart antenna technology is allowing both access points to broadcast to their client devices at the same time without interfering with each other. So you're able to actually achieve greater than theoretical maximum in the real world. The other thing to look here is also you'll notice both of these APs are roughly getting the same amount of throughput. Whereas with the Ubiquiti, it's really lopsided. One AP is getting almost double the airtime that the other one is for double the aggregated throughput. Throw it into a situation here now we've got three APs working, same thing. Our aggregated throughput jumps up to over 900 megabits per second. Aggregated Ubiquiti throughput is still below 600 megabits. And if you look at airtime utilization, the Ubiquiti actually goes down as far as how efficiently they're using that air because of the APs and the clients stepping on each other. Where again, when looking at Zyxel, we were actually able to increase the aggregated airtime utilization even higher than when we had two APs because of how that smart antenna allows each of these devices to basically operate at the same time without interference. Also, you will notice again, the throughput is pretty evenly divided between each of these different APs, where with the Ubiquiti, it's not. And I'm not picking on Ubiquiti. You're going to see basically the same story with any non-smart antenna versus any smart antenna type of product. So smart antenna is really key for maximizing speeds, maximizing user experience, minimizing interference issues in any sort of environment where you've got a high density of users or a high density of access points. So office buildings where you've got multiple floors, conference centers, apartment buildings, hotels, things like that, smart antenna is key. So now we'll start going through non-smart antennas, start talking about some of the challenges and solutions out there and some best practices. Um, so basically, most of your access points are designed to be mounted on the ceiling. The problem that you run into is you can't always mount things on the ceiling. Sometimes you're stuck having to mount things on the wall. But the antenna pattern is optimized for that ceiling mount installation. So obviously one solution to this is smart antenna. It can optimize the antenna patterns. But if you don't want to pony up the money for smart antenna, we do offer something that sort of solves these issues. And it's what we call dual optimized antenna. So a number of our access points support this dual optimized antenna. And so what happens is instead of having one fixed antenna, we've got two different sets of antennas, one that's optimized for ceiling, one that's optimized for wall mount, and allow you to choose on a per AP basis which antenna pattern to use. So if you mount them on the ceiling, you set them to use the ceiling antenna coverage. If you have to mount it on a wall, you set that one to use the wall mounted antennas. So that's one affordable way of solving this issue. So just some general mounting tips. You know, most APs are going to be optimized for mounting on the ceiling. So you want to mount them on the ceiling, generally in a central location, because they're going to cover pretty evenly in any direction from that AP. So you'll want to mount them in a central location. And generally you want to mount them as high as possible within reason. And you're doing that to avoid obstructions. You want as much open air as possible between the client device and the access point. So by mounting it up high, it allows that signal to avoid, you know, cubicle walls, people walking around, things like that, and give it the maximum amount of open air to the access point. You want to try to avoid the signal having to pass through other objects. So in general, drop ceilings have very little attenuation. So if you've got a customer who says, hey, I don't want you drilling holes in my drop ceiling to run the cables to your access points, if code where you are allows it, simply setting the AP on top of the drop ceiling works, because that drop ceiling isn't going to really degrade that signal much. So laying it on the drop ceiling on that acoustic tile is a great way to put it. You don't want to put it on the T-bar, right, the metal, because the metal will cause some interference. You want to put it on the acoustic tile. Um, Again, if code where you are allows it, most of our APs are plenum rated. If you are mounting it above the drop ceiling, or if there is no drop ceiling on a physical ceiling, you do need to take into account ductwork, lighting, and other obstructions that may interfere with the signal, particularly things made out of metal. So you may not want to mount on the ceiling itself. You may want to use some sort of standoff, and there are companies that make AP standoffs, which will drop down from the ceiling so you can avoid placing your AP between, an HVAC vent and some conduit. So hotel strategies. The typical way of doing hotels has been for a long time what we call umbrella coverage. You mount the AP in a hallway between rooms and you have one AP covering multiple rooms. So for most mid-tier and higher hotels, they're now trending to putting one AP per room or one AP every other room. The reason they are doing that is simply because umbrella coverage just doesn't work that well, especially now that you have so many devices in that hotel room. Back in the day, you had, likely it was just a business traveler. He had a laptop, he got on the Wi-Fi and sent emails. These days, he's probably got a laptop, he's probably got a cell phone, he wants to connect to Wi-Fi. If there's a family, they've got kids, each kid has their own tablet, they want to stream Netflix, Disney Plus. So you very quickly overwhelm an AP when you're using one AP to cover 4 to 16 rooms, which is how it was traditionally done. So to solve those issues, they're going with lower powered APs in the room. And just about every vendor, including us, makes APs specifically designed for this scenario. Some other things to keep in mind. Um, Look for ways or mounts that are tricky to uninstall or can lock, because people will steal anything that they can reach in a hotel room. So you want something that locks, or at least not obvious how to unlock it. So most of our locks, for instance, require you use a screwdriver or a chopstick and thread it between the AP and the mounting bracket to release the mounting bracket. Um, you also want to be sure you can turn off the LEDs on the access point, because nobody wants to try to sleep while there's a bright green or blue LED flashing at them from the ceiling or from the wall. When it comes to the wider open public areas, basically what you want to think about usually isn't so much the physical area, but user density. How many users are going to be on the APs in that area, and plan based on that. The more users or the more active those users will be, the more APs, right? So if you've got an area like a business conference room where you're going to have, 20, 30 people in there all connected, you're going to want more APs than maybe out in a public area like a lobby where you may only have a handful of people getting on the internet at any one time. So take into mind, what that area is being used for and how many users you expect to see on there. Use load balancing and client steering to avoid AP overloads, and provide different areas with their own coverage. So plan the coverage for the lobby separate from the in-store bar or the in-hotel bar versus the pool. Plan each of those independent of each other. And in any areas where you're going to have a lot of interference, use smart antenna. So when it comes to schools, you need to find out what sort of classrooms these are. So generally, every classroom needs Wi-Fi of some sort, but there's a difference between, say, a smart classroom where it's mandatory that everybody uses a Chromebook or a tablet, um, and one where it's just there as an option for kids to use to get on the internet during open, study sessions. There's also a difference between something where those devices are just being used to access the internet versus some rooms, some smart classrooms where the teachers are constantly streaming video, And instead of, playing a movie on a projector onto a screen, what they do is they stream that video to every single device. So ask a little bit about what those rooms are being used for. And obviously, the more demanding the situation is, the more APs you need in that room. Let's see here. Right. So basically, teachers and students in general should be on different networks. So you want to have different SSIDs for both and use VLANs to isolate those networks. In cases where teachers are, broadcasting and pushing content to student devices, you may need to architect the network differently than if they're generally separate from each other all the time. In a general rule, though, in classrooms of about 20 students, you want to use 2 APs per classroom. And if you're getting 30 or more devices or students in that classroom, you definitely want to use smart antenna. So let's talk a little bit about 11AX, aka Wi-Fi 6. Now, I do have a different webinar we do where we just talk about our Wi-Fi 6 products. We get a little bit more in depth into what Wi-Fi 6 does. So if you want to learn more, that's a webinar you might want to attend. Just in general here, basically Wi-Fi 6 is the first new standard that's designed to work on all frequencies. So a lot of people don't know this, but 11AC products only do 11AC on the 5 gigahertz radio. That 2.4 radio is still using 11N technology. So with Wi-Fi 6, the 2.4 radio now gets all the benefits of these new technologies on the 2.4 radio. It also allows us to use Wi-Fi 6 on different spectrums. So for instance, there is going to be something here called Wi-Fi 6E, which uses a new chunk of spectrum in the 6 gigahertz range. It's been recently opened up for end user use. Wi-Fi 6 was basically designed from the ground up to solve a lot of the issues we talked about earlier in today's webinar. So it's designed to solve those issues with inefficient use of airtime, to help try to solve those issues with drop packets when multiple devices broadcast at the same time, et cetera, et cetera. So the key technologies here are 1024 QAM, OFDMA, both upstream and downstream, uplink MIMO, spatial frequency reuse, TWT, a bunch of these new tags. So the official IEEE spec technically hasn't been approved yet, I don't think. It was scheduled to get the final vote in February. The IEEE website still says final vote expected in February. So I'm not sure if the actually voted on it yet or if it got delayed. But it's essentially good enough. A key thing to keep in mind here, though, is a lot of products out there advertising themselves as Wi-Fi 6 aren't capable of actually getting Wi-Fi 6 certified because they don't support some of the mandatory features that are part of Wi-Fi 6. Basically, in a rush to be the first to market with a Wi-Fi 6 product, people used early generation chips, which don't support all of the features which ended up becoming part of this now final or semi-final spec. And there's no way to upgrade them to be compatible. So a lot of this first generation stuff that's out there are missing key features that are mandatory as part of Wi-Fi 6. Now, the same sort of thing happened with 11N back in the day, but back then a lot of the manufacturers were open about it and labeled their products pre-N. With Wi-Fi 6, for the most part, they just labeled their products Wi-Fi 6 and hope you don't notice that some of these key mandatory features aren't actually supported. So this happened to a lot of products that are out there. Some early Cisco and Meraki Wi-Fi 6 products are using these Gen 1 chips and don't support these features and never will. And while my chart here is the Qualcomm difference between Gen 1 and Gen 2, it's similar for Broadcom and other chipset vendors. But it's not just old stuff that's been out there. For instance, Ingenius's current Wi-Fi 6 products don't support the full